Hello Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on the ZyBooks Section 1.10, just titled More Nested Quantified Statements. Alright, so this one should be pretty short. You've already seen what nested quantified statements are, nested quantifiers. And hopefully you recall that the order in which the quantifiers come in makes a difference, right? If you have an existential before a universal, that'll have a totally different meaning than a universal before an existential. So in this section, you're just seeing how to express different things with quantifiers, right? Just more nested quantified statements. So the first part of this is how to express the statement, everyone else, right? It's everyone but yourself, right? Or there's this person, and then everyone else, right? You recall from last section, a statement like this: for all x, for all y, m of x, y. There's some predicate. This means that for every pair x and y in the domain, statement m is true. That pair could be the same two values, right? But what if you don't want to include a value, a pair of values that are exactly the same, right? What if you want to talk about someone and then someone else, right? Everyone else. So yeah, so it says here the statement, so they give an example, right? A scenario where the domain is a group of people who are all working on a joint project. Define the predicate m of x, y to indicate whether x sent an email to y. Right, so m of x, y means that person x sent an email to person y. So if person x and person y are the same person, that just means they sent an email to themselves. Right? Then again, this statement, for all x, for all y, m of x, y, asserts that every person sent an email to every other person, and every person sent an email to himself or herself. Right? Because it's the same. You take any pair of people, any pair from the domain. So the names of the people could be the exact same. Agnes and Agnes down here. They sent an email to themselves. Right? So every person sent an email to every other person, and every person sent an email to themselves. How could we use logic to express that everyone sent an email to everyone else without including the case that everyone sent an email to themselves? So the idea is to use the conditional, right? Say that, if x is not y, right? So if the pair of people are different, then they sent an email to each other, right? If x is not y, then person x sent an email to person y. This says that, person x sent an email to every person y but themselves, right? And they also could have sent it to themselves, but this also, this statement here just tells you that a person x for sure sent an email to a person y, right? A person that wasn't themselves. Right. So their example here gives this table with emails and all that. Like, so we want this kind of thing where notice how the people, Agnes didn't send an email to Agnes, to herself. Fred didn't send an email to himself. Sue didn't send an email to herself. And Marge didn't send an email to herself. But Agnes sent an email to Fred, Sue, and Marge. Fred sent an email to Agnes, Sue, and Marge. Everybody sent an email to everyone else but themselves. All right. So you see how this first statement is false, right? Because of the people that don't send emails to themselves, right? Fred didn't send an email to himself. Marge didn't send an email to herself. But this statement, with the implication, with the x not equal to y implies mxy, this would be true, right? because for all the Agnes, Agnes, Fred, Fred, Sue, Sue, Marge, Marge, the hypothesis is false, so the whole thing's true, so it's still good for those pairs. And then for every other pair, the hypothesis is true and the conclusion is true, so the implication is true. So this is true for any pair x and y. Alright, so let's take a look at an example. So it's a similar setup where with sending emails, right? X sent an email to Y for in this table. The domain is this group of workers: Agnes, Fred, Sue, and Marge. And looking at that table, we're supposed to indicate whether the following statement is true or false for the group in the table. Everyone sent an email to someone else. Someone else. All right. So everyone sent an email to someone else. Right. So Agnes, now it says someone else, right? So just everybody in the group sent an email to another person, right? So Agnes sent an email to Sue, that's someone else. Fred sent an email to himself. That's not really someone else, is it? So this is false because of Fred. Fred did not send an email to someone else. Sue did, right? Marge, and Marge sent one to Fred, but Fred did not. So this is false. The only person Fred sent an email to was himself. Did not send an email to someone else. So now the next question about this here is this nested quantified statement. Is the statement, for every x there is a y, m of xy. Is this true or false for the group in the table? Alright, so I'm going to leave this up, and we'll bring up some paper here on screen, and I'll move it so that we can actually see some stuff. No, it's actually, sorry about this. Let's move it so we can see the whole table. There we go. Alright, so I got this paper out now, and let's write this statement. They're saying for every one of these employees, right, for Agnes, Sue, Fred, and Marge, for each one of them, there is a person in this group, Agnes, Sue, Fred, and Marge, such that, person X sent an email to person Y. Right. So this starts off with a universal quantifier. So this is a universal statement, meaning the whole thing has to be true for every single person in the group. So I'll start with Agnes. All right, I'll start with Agnes. So let's say X equals Agnes. And then we'll go through, for Agnes, is there another person that Agnes sent an email to? Now, it doesn't mean another person, right? This is just, is there a person? There is a Y. So, looking at the table, looking at the Agnes row for X, yeah, Sue, right? There is Y equals Sue, and M of Agnes Sue, I'll just say M of XY is true there, right? But that's just for Agnes has someone in the group that they sent an email to. How about for X equals, Fred? Does Fred have someone in the group? Again, someone. It doesn't say someone else. It just says for everyone in the group has someone they sent an email to. So Fred sent an email to Fred, yes. If I let X be Fred and Y be Fred, then M of XY is true. Right, I'll put T for true. How about for Sue? If X is Sue, is there a person, for everybody, there is a person in the group that they sent an email to? Well, yeah, Marge. Right, for X equals Sue and Y equals Marge, M of XY is true. And finally, for X equals, Marge, right, Is there a person Marge sent an email to in this group? Yes, Fred. Y equals Fred. And m of x, y would be true. So for every x, all right, this is every possible value of x here. For every x, there is a y, such that the statement m of x, y is true. So this is true. All right, this is true back here. Meaning that these statements are not logically equivalent, right? This statement, everyone sent an email to someone else, was false. But this statement, everybody basically emailed somebody, right? This is everybody in the group emailed someone, not someone else, just everyone emailed someone, even if it's themselves. This is true. They have the different truth values, so they're not logically equivalent. They're not the same statement. All right, now let's consider this statement. For all, so everyone in the group, for everybody in the group, there is someone in the group such that, that second person, that y is not the same as the first person, and they got the first person sent an email to the second person. So consider this statement in the two-player game. All right. So if they pick Sue, all right, the universal player, if I pick Sue, is there a person y when x is Sue that satisfies this statement? So that is not, someone's not Sue and Sue sent an email to them? Yeah, Marge. All right, there's a person that's not Sue, Marge, and Sue sent an email to them. Both of those are true. Okay. And now again, you could do this on your own. I'll leave this to you. Is this statement true or false for the group in the table? So this is saying, everybody in the group, everybody, so you have to go through Agnes, Fred, Sue, and Marge for the X's. Everybody in the group has some person in the group, it could be themselves, such that they're not themselves, and they got an email sent to them. Right? So again, you can fly through and try that on your own. All right, so there's another one, another email one, with Sandy, Jen, Frank, and Gary. Another kind of table. So indicate whether the following statement is true or false for the group, right? In this table, everyone sent an email to someone else, right? Someone else. Sandy sent an email to Frank, and that's not Sandy, so it's true. Jen sent an email to Frank, and that's not Jen. Frank sent an email to Gary, that's not Frank. And Gary sent an email to Jen. Yeah, that's true. Everyone sent an email to someone else. Not everyone else, just someone else. And then is the statement, everybody in the group, for all x, there is a y such that x is not y and mxy true or false? Well, this is that statement. Everyone sent an email to someone else. This is saying everyone, sent an email to a person who wasn't them, right? Sent an email to a person, there exists a y, who wasn't them. So they mean the same thing, they'll both have the same truth value. Right, and again, you can go through the different names and plug in different names for the variables and see that you're going to find for every value of x, when x is Sandy, you'll find a y such that these are both true. When x is Jen, you'll find a person in there where both of these are true. And Frank and Gary, right? All right, and again, I'll leave you to the last one. All right. This next part is on expressing, that something is unique, something is the only one. All right. So an existentially quantified statement evaluates to be true even if there is more than one element in the domain that causes the predicate to evaluate to true. Right? When you say there exists, that means there's at least one. Well, what if there's only one, right? How do you express that? How do you say there is exactly one element in the domain that satisfies a predicate? So if the domain is a set of people who attend a meeting, for example, and the predicate L of X indicates whether or not person X came late to the meeting, then the statement, there exists X such that L of X is true, if there are 1, 2, or more people who came late, right? This means that there's at least one person who came late. Now what we're doing here is expressing that I want to express that exactly one person was late to the meeting. All right, and I'll write this out as well, and then I'll go through the animation with you too. All right, so I want to express this. Now, to express that exactly one person is late to a meeting, we can do the following. That means that if exactly one person was late, that means there was at least one person, right? So there exists a person, say a person X, such that they were late, right? So I started off like I normally would, right? Such that they were late, but I need nobody else to be late either, right? I want this person X to be the only person who was late to the meeting, right? Exactly one. So and for everyone in the group, right? And this is kind of ties into what we said earlier. I want to express, everyone else, right? For everyone in the group, right? So for everyone in the there is one person in the group who was late, and if I look at everyone in the group, this is like quantifiers within quantifiers, and you'll see later that we can actually pull this one out. If this person, if the person that I'm looking at is not the same as the person I'm looking at here, right? If person X is not the same as person Y, then they were on time, right? Then they were not late. It implies that they were not late. I'm sorry, it should be Y here, because I'm talking about person X was late, and all other persons Y. If person Y is not person X, then they were not late. And lots of parentheses, I think. There we go. This is how to express that, exactly one person was late. Now you could also, since this first predicate doesn't depend on Y, you could pull this out here and say, or there is a person X such that, for every person Y, person X was late, and then this stuff, right? And if person X is not person Y, then person Y was not late, right? If person Y is somebody else, anybody else was not late. Right, you can do that as well. Like well, there's a part of the section where it talks about when you can pull quantifiers out front. Okay. Now this is a very long-winded, fancy way of saying that exactly one person was late. Now this isn't in your ZyBooks text, but it is in a video that I posted in Canvas from YouTube. A simpler notation for this that you'll see in a lot of other textbooks. If I want to say that there is exactly one person who is late, you'll see this quite often just to save on writing. There exists, and then an exclamation point after it, and then your variable, right? So this means there exists exactly one X, such that they were late. This is the same thing as all this. All right. But if you ever see an exclamation point, like you will in one of the videos I found on YouTube, if you ever see an exclamation point after a there exists an existential quantifier, this means there exists a unique there exists, exactly one or a unique x. Right. So hopefully that all made sense. Right? I know it's a lot of symbols. Right? I get this can be a little jarring because of all the symbolism. Let me go through it one more time. So there's a person at this company, call him X, such that, that person X was late. So say Bob was late. Bob is person X. And look at all the people at the company again, but this time look at all of them. If a person in the company is not Bob, then that person wasn't late, right? If then, meaning everybody else, right? Everybody but Bob was on time. Only Bob, right? Only person X. So again, hopefully you can make some sense of this. It does get a little gaudy. And you can play the animation here if you wish. All right. And they're doing the same thing that I was just describing to you. There is, so there's at least one person, right? Someone was late to the meeting. There exists X such that L of X. Need a way to express that X is the only person who was late to the meeting. So again, the parentheses, they were late. Someone was late, and if you're not that someone, right? If for every y, if y is not equal to x, then y was not late. If you're not that someone, if you're not Bob, then you were not late. Right? Lots of hopefully it's not too confusing. All right, so let's look here. Table again. Now this time, L of x indicates whether a person was late to a meeting. All right, and the domain here is just these four people: Shirley, Rob, Ted, and Mindy. So first we have to indicate whether the following statement is true or false for the group in the table. Exactly one person was late to the meeting. Nope. Two people were late. Rob and Mindy. Right, it says true for L of x. So that's false, right? Exactly one person was late. That's false. How about if x equals Shirley? Right, so we're looking at Shirley here. Is the following statement true or false? So this is L of Shirley. So Shirley was late, and all this. Well, you got the and here. Remember, an and statement is only true when both the statements that put together are true. L of Shirley is false, so I don't even have to look at the rest of the stuff. This is a false statement. But this is really saying that Shirley was late, and if a person wasn't Shirley, then they were on time. So this is a way of saying that Shirley was the only person who was late. Was Shirley the only person late? Well, no, Shirley wasn't even late. So that's a false statement. And then this one here, L of Rob is true, and for all the people, if they aren't Rob, then they were on time, then they were not late. Well, that's false because what about Mindy, right? Mindy is not Rob, true hypothesis, and Mindy was late. So false conclusion. Not true, but false. So this is not true for all y. It's not true for Mindy. So L of Rob is true, but this is not true when y is Mindy. So you have this is a false statement. Again, the way this is a symbolic representation of saying that Rob was the only person who was late. Right? This is saying Rob is late, and anyone who wasn't Rob, if they weren't anybody in the company, if they weren't Rob, then they were on time. Well, again, Mindy doesn't satisfy that, so this is false. Right? Okay. All right, so something similar here. I'll just let you work on that. Moving quantifiers, I talked about that a little bit. Remember on my piece of paper here how I moved this quantifier for all y out in front of the statement. Notice I didn't move it in front of the whole thing, right? The order that things come in matters when it comes to quantifiers. You saw that in the last section on nested quantifiers. If a there exists come first and then a for all, that means something totally different than a for all, than a there exists. Right? So, they go through this example here. Basically, if if you look at this statement, the for every x, if a of x, then there exists a y such that m of x y. Since y does not appear in any predicate before, the predicate a of x, this there exists y can be pulled out front, but again, not in front of the for all, but just out in front of the implication. All right. And they're making that same note that you saw in the last section, right? Don't move a quantifier in front of another quantifier, right? The order matters. So like for all x, there exists y is totally different than there exists y for all x. Right? Totally different statements. You can't just switch them. All right, and they go through an example here. I'll let you watch that animation. And then we just have one final thing here where you're asked to write what the English meaning would be for all these logical statements, right? all these quantified statements. So I'll just do a couple of them. Match each proposition to the corresponding English sentence. The domain is a set of all students in a math class. The two predicates are as follows. Right, so P of XY is person X knows person Y's phone number. And then predicate H of X is just simply student X has the homework assignment. So this first one is for every X for every Y. So for every pair of students, right, even a student and himself, student X knows student Y's phone number. So every pair of students, so everybody in the class knows everybody else in the classes, even themselves, of course, phone number. So every student knows every student's phone number. Yeah, that'd be that first one. Let's do one more of these. Here, one involving H. How about this one here? So this is, I'll do one. Do the fourth one because it starts with a there exists. So it says there is a student called X. There is a student in this class, such that for everybody else in the class, H of X, meaning student X has the homework assignment, and student X knows student Y's phone number, and student Y is every student Y. So there's a person in the class who has the homework assignment, and that person knows everybody else's phone number, everyone's phone number. So there is a student who has the homework assignment and knows every student's phone number. That's this last statement here. And you can fill in the other two. And then you get into the additional exercises. Again, you've seen nested quantifiers. This is just further examples of a couple more complicated ones, right? How do you say someone else or everyone else? How do you say exactly one in these notations? You see the solutions and the additional exercises. Some of these are assigned in assignment 2, some are not. I would recommend going over as many as you possibly can. Try to do the ones that I assigned, of course, right? You're going to need to do those when you submit your assignment. But do the other ones that I didn't assign too, and check the solutions and see how you're doing. Right? Practice, and please do the problems. Try to do them. Try to figure them out before you look at the solution, because you're not going to learn anything if you just look at the solution and copy it. All right. Actually try to learn something. That's the whole reason for being in a course, right? And that's all I got there for section 110 on more nested quantifiers, more nested quantified statements. And thanks for watching.